Good morning. We were in the middle of the two lectures on thermal shock, so I want to finish that up today so we can get started on the case studies. And we were right here talking about damage resistance theory. So where we left off, we were just talking about this. I'd like to just repeat this and look at another comparison of RST and R4 prime. So RST and R4 prime were the two important R parameters for describing thermal shock. R4 prime described thermal shock for materials with shorter crack lengths. RST was for materials with longer crack lengths. And I wanted to show you how you can compare these in two different ways. First way, we went over this very quickly at the end of last class, was based on stored elastic strain energy. So this is RST and R4 prime, and RST was the fracture surface energy divided by the thermal expansion coefficient squared, Young's modulus, and this was all to the 1/2 power. And R4 prime had the fracture surface energy in it, Young's modulus, and then the fracture strength squared, and then Poisson's ratio. So the thermoelastic stress for linear restraint in one dimension, the stress just equals the expansion coefficient, which is a function of temperature times the elastic modulus, or more simply, strength squared is approximately equal to the thermal expansion squared and the Young's modulus squared. Or if we just rearrange this, we can have it in terms of the strength squared divided by the elastic modulus, approximately equal to the thermal expansion coefficient squared times the elastic modulus. So we can substitute for the strength squared over E for A squared times E in the RST equation right here. So RST is approximately equal to the fracture surface energy times the elastic modulus divided by the strength squared, and that's all to the 1/2 power. So if we look at RST and R4 prime, and we divide the numerator and the denominator of both of these equations by E0, we can show that RST and R4 prime are both proportional to 1 over this term, sigma F squared over E0. So the strength squared over the modulus. So they have the same general relationship in terms of strength and elastic modulus. And this term here, the strength squared over E, is basically the stored elastic strain energy. So you minimize this term in the denominator, you maximize either one of these. So you need to minimize the stored elastic strain energy to get a high value of RST or R4 prime, which is what you want for thermal shock resistance. So we, in previous lectures, looked at the stored elastic strain energy, the work per volume equals U, the stored elastic strain energy per unit volume. And that's just the area under a stress strain curve, 1/2 sigma epsilon. And sigma is the normal stress, epsilon is the normal strain, and the stored elastic strain energy is commonly reported in calories per cubic centimeter or joules per cubic meter. And that's the driving force for fracture. So if you minimize the driving force for fracture, you maximize either RST or R4 prime. And I showed this slide before, but the area under a stress strain curve, sigma versus epsilon, is 1/2 sigma epsilon. And if we rewrite that in terms of this expression, sigma equals epsilon E, the strength equals the strain times the Young's modulus. We can put the stored elastic strain energy in this term here, 1/2 sigma squared over E, which is this term here. So it's just rewriting the stored elastic strain energy a little differently. And again, both RST and R4 prime are proportional to 1 over sigma F squared over E0, which is the stored elastic strain energy. So in short, you maximize either RST or R4 prime by minimizing the stored elastic strain energy. And how do you do that? Reducing the strength. This term here minimizes the stored elastic strain energy. And reducing the strength, well, you have a couple choices. Create larger flaws. So you introduce larger aggregates. You can also introduce porosity. So aggregates and pores are basically the flaws in refractories. And I mentioned at the end of last class, the ideal microstructure for a refractory, when you look at this delta T versus crack length curve, is at the minimum in any of these curves. So that puts you in this quasi-static crack growth mode to the right of any of these minimum values. So if you start at the minimum in the delta T versus L or crack length plot, you have to control the grain size and the population of flaws, either pores or microcracks. So you have to control the flaw size and the flaw density. Another way I wanted to point out, looking at RST and R4 prime, here's our two equations again. Here's our stress for total linear restraint in one dimension. So we can square each side of this equation and get sigma F squared is approximately equal to the thermal expansion coefficient squared and the Young's modulus squared. If we rearrange this equation, we can show that E over sigma F squared is about approximately equal to 1 over E and then the thermal expansion coefficient squared. So we substitute this expression 1 over E A squared for this one in R4 prime, E0 over sigma F squared. And if we do that, R4 prime becomes the fracture energy divided by Young's elastic modulus, the thermal expansion coefficient squared, and then 1 minus 2 times Poisson's ratio. So both RST and R4 prime are both proportional to 1 over E A squared. So they both have the same dependence on thermal expansion and Young's elastic modulus. So it would be nice to have a material with very small thermal expansion coefficient that would maximize RST and R4 prime. But unfortunately, we don't have materials with extremely low thermal expansion coefficients. So you can maximize RST and R4 prime by trying to minimize the thermal expansion coefficient, and that minimizes the stored elastic strain energy and gives you the higher values of RST and R4 prime. So this thermal expansion coefficient in the denominator of either RST or R4 prime, like I said, you don't have a lot of control over that. If you had a 0 expansion coefficient, you have 0 stress levels as you change the temperature. That would be the ideal situation. You try to use materials with low expansion coefficients. That gives you lower stress levels as you increase the temperature. And then when you have high thermal expansion, you're going to have higher stress levels with temperature changes. So I showed these next three plots in a previous class, but this is percent expansion versus temperature. And this goes from 0 to about 2%, room temperature to about 2000 degrees C. So these are simple oxides like MgO, CaO, Al2O3, Cr2O3, and ZrO2. And they have pretty high thermal expansion coefficients. Quartz is also on here with the transition right there. So you don't have a lot of choice. These are all refractory type materials. And for comparison, this is where vitreous silica is. You can see how low it is, but this curve does not extend really much past 1,000. So it's a low temperature material. So we're kind of stuck with these higher expansion materials. Same plot for binary and ternary oxides, expansion versus temperature. This spinel type structures. This is actually spinel MgAl2O4, another spinel, another one, a calcium silicate and a magnesium silicate. This is phosphorite, and this is zircon. So these compounds, common refractory materials, are also fairly high. This one, Al6Si2O13, is mullite. It's getting lower, so mullite has some advantages for thermal shock. And then this is the cordierite, the magnesium aluminosilicate. It's pretty low, but again, it's only useful to about 1200 C. So mullite and perhaps zircon have lower expansion coefficients. Zircon has some higher temperature issues where it dissociates into zirconium silica. And then the non-oxides, they're lower. You can see graphite, whether parallel or perpendicular to the basal plane, and amorphous carbon, they're getting a little bit lower along with silicon carbide. So I just put these plots to show that, well, you're pretty much stuck with certain values of the thermal expansion coefficients, and they're either intermediate or higher. So in terms of fracture or refractories, the first three items here, we've already discussed how to measure K1C. We mentioned G1C, and now there's another fracture surface energy for fracture initiation, gamma NBT. This is the fracture surface energy to start a crack moving. So these parameters, K1C, G1C, and gamma NBT, are based on linear elastic fracture mechanics. And then the nonlinear elastic or plastic fracture, there's something known as a J integral, which is J1C. It's similar to G1C, but it accounts for nonlinear behavior. There's another fracture surface energy that's very important, gamma WF for work of fracture. And by the way, NBT is notch beam technique. And that's the technique I showed you to measure K1C. This is the energy, gamma WF, to keep a crack moving once it starts. So it's the energy to propagate a crack. And then R curves, which I mentioned briefly, the R versus crack length, the change in crack length, delta C. You want rising R curves, and that's where you have some nonlinear behavior. So high values of J1C, high values of gamma WF, and rising R curves all give rise to better thermal shock resistance. the most common measurement, the easiest measurement is gamma WOF. So that's a pretty easy measurement. People rarely use J1C or rising arc curves because it's a lot more effort to make those measurements. So I showed this simple bend bar, single edge notch beam bend bar to measure fracture toughness. So the lower span is L. So there's two knife edges for the lower loading points, and then the midpoint is loaded with a third knife edge. We have an initial flaw size or notch C, and P is the load, L is the lower span, B is the sample width, H is the sample height, and C is the crack depth. And this is the equation I showed for K1C. It has units, megapascals times the square root of meters. So K1C is a function of the load, the span, the crack size, the sample dimensions, B and H. And then there's additional functions that I showed previously relating C and H, and then also the span and the sample thickness. So pretty straightforward, single edge notch beam, loaded to failure, put in these variables, you can calculate K1C. And then the strain energy release rate, G1C, is given by this equation here. So once you get K1C, you have to calculate Poisson's ratio independently and Young's modulus independently. You can get the strain energy release rate. So G1C is a critical strain energy release rate to initiate fracture, to start this crack moving. It has units, joules per meter squared. So once you determine K1C, you get these two elastic constants, nu and E. You can calculate the strain energy release rate. And then this other fracture surface energy is calculated from the same sample, the notch beam sample. So gamma MBT just equals G1C over 2. Is everybody okay on connection with today's lecture? Or am I losing everybody with the bad connection?
No, you're good.
You're good.
Okay,
Okay, so it's just me.
yeah, maybe. I don't know how to fix that. Maybe you can, I don't know if you can log in again or try to get a better connection.
Yeah, I can always pick it up on the recording, so we're good.
Okay. So this gamma MBT is actually what's commonly measured and used when people are looking at making these types of measurements to improve their thermal shock resistance. And I like this measurement. I've used it. Not too many people use it, but I like it. And I thought I'd mention it because it's sort of equivalent to G1C, but it addresses the nonlinear portion of a stress strain or a load displacement curve. And you can use J1C also to predict thermal shock behavior. So it's pretty simple measurement. You take a sample with a notch, just like we do for K1C, and you generate a load displacement curve. So this is load and this is delta, load displacement curve. And you have a stable situation where you have a maximum and then you start to decrease the load as the crack extends. You then take an unnotched specimen and you load it to this Pmax right here. So this is the total energy, elastic and inelastic. This is the elastic energy, the difference here. is J1C. So this is the nonlinear portion of the inelastic processes taking place in the crack process zones. So the bigger this value, the better the thermal shock resistance. So the frontal region of an extending crack, there's micro cracking, plastic deformation. In the wake region, there's aggregate bridging and so on. So what happens in the crack process zone that's inelastic is going to show up in this type of measurement. So J1C is a path-independent energy line integral. It encompasses the entire crack tip. It has the same units as G1C, joules per meter squared, but it measures the total energy, elastic and non-elastic, during fracture initiation and growth of the crack surface area. So you can separate out the elastic and the inelastic portions using this approach. So in this equation here, you have B is the unnotched ligament in this sample here. In the unnotched sample, B is the thickness. So you measure this unnotched ligament, small b, the sample thickness B. You measure this area, and that's just this area minus this area. So you generate these two load displacement curves, measure these areas, take the difference, and that's AG. So it's basically calculated from the difference in these two energies. So if we have a perfectly linear elastic case of brittle fracture, it turns out J1C equals G1C, which equals this term here, K1C squared, 1 minus nu squared over E. I like this measurement. I've used it. It works, but it's tedious, and like I said, the work of fracture measurement is much easier, and that's what people mostly use. So the fracture surface energy, gamma WF, is the work of fracture. It's usually measured in 3-point bending, and it's just the integral of the load displacement curve, the area under this load displacement curve, divided by 2 times the fracture surface area A. So the work of fracture is the fracture surface energy to propagate a crack. So that's the energy to keep a crack moving. It's in joules per meter squared. P is the load, X is the displacement. This integral PdX is the work to create a new fracture surface. And then A is the area of a fracture surface. So this is usually measured in what's known as a chevron notch bend bar. So you cut a notch and you leave this pointed or triangular ligament. So area A is still intact, and you cut away these 2 triangles on either side of A. So it's 3-point bending. You have your lower knife edges, your top loading point. So P is the applied load, W is the width of the sample, H is the height, and you have to measure this area A. Well, that's the area in this equation right here. So this configuration, it really promotes stable crack growth. You're concentrating the stress right at the tip of this triangle, and as the crack moves upward, it just keeps seeing a bigger and bigger area, and that forces it into a stable mode. So this is what you want to generate in a work of fracture test. This is the load versus displacement. And so you want to load it, you want it to bend over, and then it has this long tail, looks something like that. So you don't want a brittle fracture, which would be a straight drop, vertical drop. You want this very stable fracture. So the area under this curve is this integral PDX. So you measure the area under the curve, and then you measure the area of those triangles, and you can get the work of fracture. So again, P is the applied load, X is the displacement. This integral PDX is the work to create the new fracture surfaces. It's the area under this curve, and A is the area of the triangle in this chevron notch. So in a material that has high work of fracture, you're usually running at a very slow crosshead speed. It may take a half hour to an hour or even more to generate a curve like this, so it takes some time. So that work of fracture test is usually run on smaller bars. These are typically 1 by 1 inch in cross section, maybe 6 inches long. There's a second test, a wedge splitting measurement test. And this one, this would be it could be a half of a brick, it could be an entire brick. It's a much bigger sample. And you cut a notch in it, you put these wedges, you put these cylinders, and then this is the wedge that you load. You put a starter notch on one edge. So you load this wedge and it splits the sample apart. It's basically the same as work of fracture, but it's done in a controlled mode again. So the starter notch keeps the crack from wandering out of the plane here. And the advantage here, it's a much bigger sample. This is a much smaller cross section compared to a half of a brick or even a whole brick. And why this is relevant is because of that wake process zone. If it's extremely large, you need a large sample. A lot of the early work on these work of fracture samples, I believe, is questionable because of the large crack wake process zones cannot be measured in these short distances, whereas this test has an advantage. And I've actually done some tests where I vary the size of this notch in the last couple of years, and I can see the bigger the sample here, the bigger the work of fracture, just indicating a large wake process zone. So keep in mind that you need a fairly large sample, whether if you're running work of fracture or wedge splitting, especially if it's got good thermal shock resistance. You want to measure all of that energy for the work of fracture. So this is what a wedge splitting test might look like, a load displacement curve. So this could be a very high duty fire clay with a great deal of glass present. So it's kind of a brittle refractory. So when you load it, you get linear behavior, then failure, an abrupt drop in the load. But if you have an opposite type of sample that's thermally shock resistant, like a highly microcracked alumina, you get this stable crack growth. So here's where your nonlinear behavior takes place. So this is considered brittle. This would be a tougher material. So the advantage again of wedge splitting is you're going to a much larger sample size. And then we also mentioned these R curves. I showed a method, a graphical method of making those measurements. It's also a tedious measurement. And this portion here, where the R curve is rising, was the nonlinear portion. So the nonlinear region of a stress strain curve or a load displacement curve is deviation from linear elastic behavior. So this is what you want for a material that has good thermal shock resistance. You need a rising R curve. A flat R curve would be a brittle material. So again, this is a tedious measurement generating a GR versus delta C curve. J1C is kind of tedious. So the gamma NBT and the gamma WF are what's commonly measured. So we've been talking about a fracture surface energy, gamma F. We put it in the numerator of R4 prime and RST, but we never really said what this fracture surface energy is. And it turns out there's three different types of fracture surface energies. Gamma F in this equation is not the thermodynamic surface energy. So surfaces have unsatisfied bonds, so they have higher energy than interiors of a material. So the thermodynamic surface energy is the energy necessary to create a unit area of new surface. That's a pretty low number, 1 to 2 joules per meter squared. So gamma F is not the thermodynamic surface energy. We just looked at gamma NBT, the fracture surface energy to start a crack moving, to initiate a crack movement. That gamma F in these two equations, R4 prime and RST, is not gamma NBT. Gamma NBT is typically 10 to 20 joules per meter squared for ceramic materials. But gamma F in these two equations, R4 prime and RST, is gamma WF. And that's the effective surface energy, the energy needed to propagate a crack. So the higher this value, the more thermal shock resistant is the material. So this accounts for all kind of crack microstructure interactions in the frontal process zone and in the wake process zone. So it's a higher number than either of these, either the thermodynamic surface energy or the energy to initiate a crack. It's usually 30 to 120 joules per meter squared, and that's at room temperature. And then at higher temperatures where the material becomes with plastic, it can be 1,000 joules per meter squared. So this work of fracture surface energy, what's responsible? What are the crack microstructure interactions? Microcrack extension in the frontal process zone, crack branching, crack deflection also in the frontal process zone. If it's at high temperatures, plastic deformation in the frontal process zone, and then crack bridging in the crack wake. So for very brittle materials like a glass or single crystals where you can fracture along cleavage planes, these three surface energies are basically the same. Gamma F, gamma NBT, and gamma WF, and in extremely brittle materials are all the same. But in our type of materials, we want to design a microstructure with a high work of fracture. Gamma NBT is always going to be low when you have a refractory material that's highly microcracked. The cracks are already there. So one designs a microstructure with a high gamma WF, and one can look at the ratio gamma WF to gamma NBT. The higher that ratio, the more thermal shock resistant is the material. So in refractories, people are usually measuring these two surface energies, setting the ratio, and anytime you develop a microstructure that has a high ratio of those two, it'll have good thermal shock resistance. So the ratio of gamma WF over gamma NBT, you want that to have as high a value as possible. When it's over 10, that means you have a refractory with takes a great deal of energy to propagate a crack relative to initiating that crack movement. So that's going to have high thermal shock resistance anytime that ratio is greater than 10. So the higher the ratio, the better the thermal shock resistance. So that then the refractory is able to accommodate extensive internal cracking and still retain its mechanical integrity. It doesn't have to be strong, it just has to maintain its integrity during the application. The higher the ratio, it usually has a material with a long tail in the stress strain curve. So going back, the longer this tail, the higher the work of fracture, the better the thermal shock resistance. So if you're making a series of refractories and you're varying the microstructure and you want to evaluate them, you can obviously run a thermal shock test. You can also make these measurements, which are pretty simple to do, to give you some insight into how you're improving the thermal shock resistance. So this is the crack process zones that I showed a few classes ago. So a high ratio of gamma WF over gamma MBT, you're activating all of these processes around the crack tip and in the crack wake. So the frontal process zone again is in this portion, right at the crack tip where the stress is intensified. You generate microcracks, they link and form longer cracks, and then they start to branch. In the crack wake, you have bridging of aggregates, and at high temperature, you have bridging of silicates, very viscous glasses. So as this crack moves from left to right, you develop this frontal process zone, but it's a steady state frontal process zone. So as the crack moves from left to right, the process zone moves with the crack tip, but it's a steady state because the crack process zone isn't growing in size. But in the wake region, this crack length keeps increasing, and basically, if you have a thermal shock resistant material, you have a lot going on, a lot of energy dissipation in the crack wake here. So I'll show why the crack wake region is more important than the frontal process zone later on today. But basically the processes that are taking place in the wake region, in this region, are more important than in the frontal process zone because this is where the energy is being dissipated. CMOD is a crack mouth opening displacement. So this opening is very small in a brittle material, but it's much larger in a refracting material because you're generating a long wake process zone with material bridging across that wake region. So aggregate bridging, silicate bridging, give this higher or larger CMOD, a larger opening here. And that's also related to the rising arc curve. So you need to develop a refractory that has both a frontal process zone, but primarily a microstructure that resembles this in the crack wake. So again, you want a high ratio, the work of fracture to the notch beam technique. Silicate bridging only occurs at elevated temperatures where the glassy silicates become viscous, they can flow, create bonding ligaments, and they're only active over a limited temperature range. Once the temperature becomes high, the viscosity decreases, the bonding ligaments are no longer strong enough to bridge and the crack wake, so there's no significant bonding. Aggregate bridging, three possible mechanisms, and you're going to need an aggregate that's stronger than the matrix. So you can have bridging across the fracture surfaces in the crack wake, wedging of aggregates behind the crack in conjunction with bridging, and then frictional pull out of the aggregates. The frictional pull out dissipates energy, so they may pull out from one side of the crack. So how do you improve crack growth resistance through microstructural design to get a high ratio here of these two fracture surface energies? Aggregate size. Aggregates have to be larger than this crack mouth opening displacement, so larger aggregate sizes. Aggregate geometry, you want very angular aggregates. They have better mechanical interlocking in the crack surfaces compared to a spherical aggregate. You can add fibers. They have large aspect ratios. They can bridge the crack. Aggregate strength is important. You need stronger aggregates compared to weaker aggregates. The aggregate surface texture, rough surfaces are preferred to smooth surfaces. Rough surfaces interact and create more friction during pull out. And chemical bonding between the matrix and the aggregates. Well, this is real important. You do not want very strong bonding between the matrix and the aggregates. If you have very strong bonding, you're going to deactivate all these bridging mechanisms, and the fracture path is going to be through the coarse aggregates instead of around them. So you have to have a interface that's not too strong. So that interface between the matrix and the coarse aggregates is real important. And generally, you know, the aggregates are pre-fired crushed materials, and the matrix is going to be weaker than the aggregates. So this fracture surface energy, gamma WF, is considered to be a material constant, similar to K1C. The rising R curve in refractories suggests the work of fracture may only be material constant for large test specimens. So that has to do with the size of the crack wake. So if the specimen size is large compared to the size of the effective crack wake process zone, then the work of fracture is a material constant. So in rising R curve behavior, the crack process zones increase in size as the crack length increases until you reach that plateau where the process zones are fully developed in the steady state condition. Most laboratory scale work of fracture specimens are not large enough to generate that plateau. So the coarse aggregate microstructure does not usually allow for a complete development of steady state process zones in small samples. That's why the wedge splitting sample on a full-size brick is much more useful. So the energy balance approach to thermal shock damage resistance can be related to the concept of rising R curves. Both are based on energy consumption by nonlinear processes in the crack wake and frontal process zone. So when a crack consumes more energy, it will not propagate as far and the thermal shock damage will be less. So these repetitive R greater than G events are responsible for the rising R curves. They're the same as its quasi-static crack growth in that energy balance approach we use to derive RST and R4 prime. And that was the energy balance approach for those two thermal shock damage resistance parameters. So the strength of refractories in a well-designed microstructure should only decrease gradually during the thermal shock. You want a gradual decrease in the strength. You don't want a catastrophic failure. So the important features of the microstructural design are related to the aggregate character, its size distribution, its strength, and then the bonding to the refractory matrix. So basically, thermal shock damage resistance in a refractory depends on how the crack interacts with the microstructure. So energy dissipation mechanisms during crack propagation are responsible for rising R curves, but they're not really considered in the thermal shock damage resistance theory. So when we derived R4 prime and RST, we had this equation for delta T, the critical temperature difference. we had the fracture surface energy in it, Poisson's ratio, the Young's elastic modulus, the crack density, the crack length. So it's not obvious, but the energy dissipation mechanisms are embedded in these two terms, the N, the crack density, and then gamma F, the fracture surface energy. So we can take this approach, the energy balance approach, and we can modify it to include these commonly measured values, gamma NBT and gamma WF. So we can relate gamma NBT to crack initiation condition in a rising R curve, and then we can relate gamma WF to the energy dissipation plateau for the rising R curves. So this was the energy balance that we used in the derivation for RST and R4 prime. We can introduce gamma NBT, and again, that's the energy to start a crack moving, and gamma WF, the energy to propagate that crack a long distance. So gamma F here now becomes the difference between gamma WF and gamma NBT. So we modify the equation, and we also put in NF and NI. NF is the final number of cracks per unit volume. NI is the initial number of cracks per unit volume. So we expand this term here, and we have an NI over here in this term minus this term where we have NF. So we have a final crack density, a final crack length, an initial crack density, and initial length. And then we have our two different fracture surface energies. So this is a really messy equation. In this derivation, they go through a series of simplifications. So they take these different terms and they put them in terms of B1 all the way to B5. So B1 equals this first term here, B2 equals this term, B3 equals this term, and then B4 is this term, and B5 is this term. So if you rewrite this equation in terms of B1 through B5, you have an equation that looks like this. It really doesn't look a lot better than this, but it is a simplified version. And when you look at that, if you assume the crack size L0 is small, you have initially short cracks. That means LF is much greater than L0. And then the following terms can be eliminated. So this term here becomes B4 LF squared minus B5 L0 squared. This term becomes 0. This term becomes 0. And then this term is approximately 0. So this equation just becomes this. Well, this equation, after you account for which terms drop out, becomes this equation here. And then the final crack length is just B1 over B4, and that's to the 1/2 power. And we substitute back in for B1 and B4. And now we have an equation for the final crack length where we have incorporated this work of fracture energy. And if we go back to our delta TC equation to initiate propagation of short cracks, this gamma F, we substitute gamma NBT for crack initiation, and we have this equation, and now L becomes L0, and substituting for TC, the delta T critical, we can then put in that into this equation, and we end up with an equation that has the final crack length in terms of the ratio of these two fracture surface energies. So this is what we were trying to do, incorporate the measured fracture surface energies into that energy balance approach. So this is the equation that we're looking for. So the final crack length is related to this ratio. It's actually the inverse of the one I had mentioned a few slides ago. It's gamma NBT over gamma WF. So the final crack length is related to this ratio, and you can relate that to the R curve behavior. So this ratio determines the final crack length. So high values of the inverse of this, gamma WF over gamma NBT, yields shorter crack lengths. So the higher this surface energy, gamma WF, the lower the final crack length. And that's because you have somehow you've increased the crack interaction with the microstructure. And also, this ratio of NBT over WF determines R curve behavior. If these two are equal, they drop out of this equation. So if gamma WF equals gamma NBT, you have a flat R curve. You have no crack interaction with the microstructure. And now you have this equation where this term, when these are equal, is 1 that drops out. So when you have a gamma WF greater than gamma NBT, the R curve is rising, it reaches that plateau, and now you have a lot of crack interaction with the microstructure and better thermal shock resistance. And you can play around with these equations. You can take the equation for the final crack length. You can solve it for the crack density. And these equations have an L0 in it. And you can calculate the crack length from a fracture toughness measurement when you measure K1C. And you can get a crack length, which is this L0. So what we've done is we've incorporated these fracture surface energies into the energy balance approach for RST and R4 prime. And we can relate them to a crack length and a crack density. So one last thing here to finish this up before we start on the case studies next class. Refractories are susceptible to slow crack growth. So the cracks can grow in size before failure takes place. And this slow crack growth can take place in a very stable manner. It can take place in service, can take place during testing. So there's two types of crack growth experiments. And one is the stressing rate experiment. It assumes we start out with small cracks. So this would be an as-produced refracting material that's micro-cracked. The cracks are relatively small. So this is an equation that describes the stressing rate experiment. The stress, the fracture stress equals a constant d sigma dt, which is the stressing rate. And that's to a power 1 over n plus 1. So n is a slow crack growth exponent. It's a parameter that represents resistance to crack growth. D sigma dt is the stressing rate. That's how fast you test the sample, how fast you move the crosshead. So if you look at this equation, 1 over n plus 1 is a constant. The faster you stress a refractory, the less time there is for the cracks to grow into larger sizes, so the strength is higher. So in this kind of experiment, you take a refractory or ceramic material, you vary the stressing rate, and then you measure the resulting fracture stress. So the log of this equation is shown here. The log of the fracture strength equals the log of a constant plus 1 over n plus 1 times the log of the stressing rate. So if you plot the log of the stress versus the log of the stressing rate, you get a curve that looks like this. So the faster you stress it, the less time for cracks to grow, the stronger it is. And the slope is 1 over n plus 1. The intercept is the log of c. So you can calculate c and n. The other type of experiment is where you have large cracks. So this would be a double torsion test. And in this test, the crack velocity equals a constant A. K1 is the stress intensity. It's not K1C, it's not critical yet, it's just the stress intensity. To N. N is the same N over here. It's the same N that represents resistance to crack growth, is the crack growth exponent. So a double torsion test looks something like this. This is a large plate. You put a starter notch, and then you load this end of the plate where the starter notch is in 4-point bending. So you have a lower loading point here and a lower loading point here. So that would be your lower span. Then on each side of this notch, you have 2 upper loading points, very similar to 4-point bending. The remaining ligament here is dn, the sample thickness is d, the width is w, and then the bending moment between these loading points is wm. So you load a sample in double torsion until it bends over, then you stop the loading, and then you watch the sample, the load relax with time. So it's a load relaxation experiment. The sample is loaded until the load does not increase anymore with time. You stop your crosshead and you watch the relaxation. So P0 is the maximum load. The initial slope of this relaxation region is P0 dot. And then any point on this curve, you can take the slope pi dot, and then that has a corresponding load pi. So the crack velocity is given by this equation. We measure P0, pi, and P0 and pi off of the this curve here. B is given by this equation, and y is the crosshead speed, y dot. So B has these sample dimensions in it, Wm, W, and D. Wm, W, and D, the sample dimensions. So we can calculate the crack velocity. So the stress intensity is given by this equation. So K1 equals the load times the sample dimension, 3 times 1 plus Poisson's ratio, and that's divided by sample dimensions, W, D, cubed, Dn, and that's all to the 1/2 power. So we can put in K1, we measure V, and we calculate N. So the log of V equals the log of A plus N times the log of K1. So if we plot the log of the velocity versus the log of K1, as you increase the stress intensity, the crack velocity increases. But the slope is now N, and the intercept is the log of A. So we can calculate an N here. So N is the same in a stressing rate experiment or in a double torsion testing type experiment. In the stressing rate, we have short cracks. In the double torsion testing, we have large cracks. So N is a function of crack length when there are microstructural interactions. So in this stressing rate experiment, we'll say N equals N micro for short cracks And in double torsion, we'll say N equals N macro for large cracks. So if we take a material like an aluminosilica refractory and we run a stressing rate experiment, we get the log of the fracture stress versus the log of the stressing rate. We get a straight line, and the slope is 1 over 1 plus N micro. And for this particular fire clay refractory, N micro is 24.5. That's the value of N. That's the value that represents its crack growth resistance. And if we run a double torsion test on the same aluminosilica fire clay type material, we plot the log of velocity versus the log of K1. We get these different curves. They're just different samples. So there's 4 different samples shown here. The slope is N macro, and it's in the 90s here. Over here, it was about 24. So it's about 4 times larger. So if we plot N micro versus N macro, this is the stressing rate experiment for short cracks, N micro for long cracks, we get a relationship like this. So what this is showing is that the longer the crack, the bigger the N value. So what that means is the bigger the crack, the higher the crack growth resistance. And that means what's happening in the wake region of the crack is much more important than what's happening in the frontal process zone. So N macro is greater than N micro. So larger cracks have greater resistance to crack growth than smaller cracks. So this is telling us the wake process zone is more important than more important in crack growth resistance. And this is what I said when I showed the diagram of the crack and its frontal and wake process zones. I suggested that the wake region is far more important. Well, I mean, what these 2 experiments show is that it actually is more important. So in the crack process zones, the frontal process zone is constant in size as the crack grows, but the wake region continues to increase in size as the crack grows. So how you design a microstructure with a long crack wake process zone is going to be a factor in the thermal shock resistance. So this is the last slide. It just how people measure thermal shock resistance. So it's pretty simple. You just measure a strength loss or a reduction in structural continuity, and that's either a sonic velocity or a Young's modulus. So you measure the loss in a property that you can measure after you subject it to thermal cycling. It's usually the standard ASTM test now is 1-inch cross-section bars, 6 inches long, thermally cycled in and out of a furnace, usually about 2200 degrees F, 5 cycles in and out, and then you measure the strength loss or the reduction in continuity. So the difference in flexural strength, which is the MOR, between uncycled samples and then samples you thermally cycled, and then the reduction in structural continuity is the loss in sonic velocity or Young's modulus before and after cycling. So this is pretty much the standard thermal shock test that's used now. When I go over the case study starting on Thursday, we're going to look at a lot of different materials, and we're going to look at ways people have measured thermal shock resistance. There's other ways besides this ASTM standard that has the 1 by 1 by 6 inch bend bars. And we'll look at a lot of different ways how people measure thermal shock resistance and how they looked at the microstructure and how they tried to improve thermal shock resistance. So that finishes up the background theory on the different properties like strength, elastic modulus, thermal expansion, thermal conductivity. The two critical R parameters, RST and R4 prime, and the two critical fracture surface energies, gamma WF and gamma MBT. So all of those parameters, those fracture surface energies, we'll look at those in all the case studies. So the rest of the course, I'll go over what other people have done to make better materials in terms of thermal shock resistance. So thanks again for listening in today, and I'll see you next Thursday. Have a good rest of your day. Thank you.